Good morning. Thank you so much for the invite and also the very kind introduction. So this morning, I'll be share some of the work our lab. And as introduced, we are a research group at the National Library of Medicine Intramural Research Program. We are interested in using AI and machine learning for both biomedical text and imaging processing. So on a daily basis, we primarily work with literature data. When access is available, we also work on clinical data recently in terms of both clinical electronic medical records as well as clinical images, particularly in the area of ophthalmology and radiology, because that's where we have a great collaboration with clinicians on the NIH campus. So using AI and the machine learning, we work on a set of different problems, ranging from improving information access in the literature to extract key information from the literature and turn that unstructured data into structured knowledge, as well as AI in medicine, where we're mostly focused on developing deep learning tools for autonomous disease diagnosis and prognosis. But for this talk, I'm mainly focusing on text part to talk about literature retrieval and information extraction. So we'll get started with a system search portal that you're all familiar with. In fact, you're all contributor to PubMed because and many of you are authors and you publish papers there. So PubMed today has over about 34 million articles, and on the average day, we have about 2.5 million users. They're doing about 3 million searches and 9 million page views. So even though machine learning is a hot topic these days, but we at NCBI have really been using machine learning prior to the era of deep learning for implementing different kinds of search assistance or features in PubMed using machine learning. So back in 2018, we actually wrote a paper to talk about the details, sort of under the hood work about these features that implemented and made available by machine learning, along with a set of best practices so that we can increase the transparency of these computational tools, computational techniques that we used, as well as so that the users can best utilize these features. So today I don't have time to go through all the details of these PubMed search features, but I do want to give you one example called the best match, so give you an idea of what we do at NCBI. So this started actually as the sort of the old PubMed back in 2017, and at that time, as you can see, that the best match results, the most relevant results were layered or displayed on top of the regular search results that are sorted by date order. So the first question a user might have is, why do you need a relevant search? Okay, so I already mentioned that there are over 30 million articles, and that continues to grow at a speed very fast, over 1 million new articles every year. That's about 2 to 3. Now it's actually close to 3 papers every minute. We already talked about maybe 5 minutes, and that's already a couple, dozens of papers that we are left behind. But you will say, not all the papers that I will read, but think about yourself as a researcher, how many people you can afford to read in a year, maybe a few hundred, right? So there are certainly topics that are very interesting to read. Just look at the COVID literature. And when we started looking at the papers, COVID literature space, there were a few hundred in March 2020. And now that's after 2 years, a little bit more than 2 years, we are reaching 250,000, okay? And that's probably the single topic, I've seen in the biomedical literature that grows so fast. Not only does the literature grow so fast, but also the user behavior is changing. Okay, so ask yourself, what was your last time actually go to the second page of Google to find something? Okay, that's certainly possible, but probably rare. But you may say that PubMed is PubMed and Google is Google, but actually PubMed users like ourselves are also using Google in our other searches, and in a way we're unconsciously are changing our search behavior. And so exactly when we look at the PubMed search logs, we find that 80% of the time that people click on articles that are in the first page, okay? And 20 is a magic number because up until the new PubMed, PubMed always return 20 results on its first page. Okay, so those two reasons, and among other things, like today's researcher is more interdisciplinary than ever before, that motivated us, in particular as a postdoc in my group, Nicholas Fiorini, to look at and to think about providing some alternative search order in addition to data sort order. So we want to bring the most relevant articles to where the most user action is, which is the first and second page of the search results. Okay, so we investigated a number of different techniques that we can use, and lastly, eventually we decided to using a machine learning technique for information retrieval known as learning to rank. Okay, the reason we picked that is because it has been suggested in the literature back in early 2000. So by the time we started to looking at, we have been using that also in our research, and many others have evaluated the algorithm in both academia as well as in commercial search engines. Okay, so it's a quite mature technique at that point. So, but as you all know, that if you're using machine learning for developing something, for developing an algorithm, you need training data, and it's practically impossible to gather a large data set where we have a query and then we have the relevant document judged by human at a large scale. That's just impractical to do that. Instead, we sort of looking for the convention by the search engine industry, which is to using the search log to gather sort of the silver standard data. So we look at every time people doing a PubMed search, they look at some papers they choose to click, we know what you clicked on. Okay, so we can look at the query put in and the articles people choose to read. Of course, we're not going to take in any individual information like that. We're looking at the queries that many people searched on and the same document that many people clicked on, and that give us the signal that this is mostly likely to be relevant. It's not perfect, but that's what we can gather for a practical application. So using machine learning, we can do better because we can now including a lot of ranking factors. And in fact, we have all features we call in the scientific community. We have about dozens of different features. So I listed some of the features here, like article type. So if it's a review article, that tend to be more important and then ranked higher, because for a lot of the general users, they may look into a new topic and they want to look at the review articles. Even though we do not rank papers strictly by date, but as a researcher, we're always looking for new papers. So when that happens, we get new recent papers a boost, but not necessarily strictly ranked just based on that information. If a paper has been accessed, has been read by many researchers, that gets a boost too. And finally, of course, we would using the basic information signal between a query and a document. Okay, that's our basic relevant signal that we always use. So all the details were published in the PLOS Biology paper back in 2018. And let's say this is an example where you see how best match relevant search in action. Okay, so let's say you listen to my talk and you thought, okay, I want to read more about this paper, but you don't remember how to spell my name. So you put keyword best match PubMed. Okay, but if you search that in the most recent mode, you don't see that paper. But if we change that mode to be best match, yes, that paper is right in the top place. And in fact, when I did this for the presentation, I also find, okay, the second paper is actually quite relevant. It talks about an external group in Canada comparing the date sort order and the PubMed best match order and how they used for systematic reviews, and they find that best match is actually working better compared to the date sort order for writing large systematic reviews in 6 different cases. So of course, I want to show you because I cherry-picked this example. But before we actually do anything with PubMed, we have to go through a rigorous evaluation. We did a lot of offline testing that I'm not showing here, but in reporting that paper, just like using the conventional matrix like precision recall, average precision, and comparing the best match and date sort order. Also, in addition, we started to show the best match implemented in the production system in PubMed and show that to about 5% of our users, or 1%, 2% at the beginning, and then 5% of users. And then gradually rolling that over to more users. And what we found is that people click more when we display search results in best match relevance mode comparing to the date sort order. Okay, we have a 20% higher click-through rate. Okay, so 20% may not be so impressive, but think about, you do a Google search, and those search engines always display those ads for you to click on. If they get a click-through rate of 1 or 2%, that's considered as a very successful ad. Okay, so 20% in that context is quite amazing, in fact. And once we roll this over to more users, we find that it has a very significant uptake by our users. We have now used by millions, and that was actually before best match is used as a default in the new PubMed. And along with a list of positive user feedback, and one of the user feedback is to put best match in the default, and that's sort of what we did in the new PubMed. So if you are a machine learning guru, you know that the learning to rank algorithm is almost 20 years old, okay? So it's not something new in the era of deep learning. So you may say, why not choosing deep learning? And there are methods like word embeddings, like BERT models. So we started looking at deep learning indeed also a couple of years ago and looking at more advanced techniques for further improving our retrieval. But I will say that at this point, deep learning is not yet implemented in a production system, but certainly we are very interested in doing research continuously with search engine like PubMed. So PubMed is great, but it is still, in the end, it's still a keyword-based search system, okay? So a lot of our users, when they use PubMed, they have information needs, that is to find me all the papers and only the papers that are relevant to a particular topic, okay? And it could be relevant to COVID-19, it could be relevant to any other topic of your interest. And what they're starting to do when they have such an information need is they put together a long list of query words, okay? And because they're trying to be precise, at the same time trying to be comprehensive. But as you can see, those two things are sort of contradictory to each other, okay? And not to mention, in some cases, especially at the beginning of the pandemic, there's no word that COVID-19, that keyword is actually not used in the literature, because the term was not coined and used by the research community. Instead, there are many different ways that were expressed or used to refer to the word COVID-19, okay? So what we really want is a system that can actually do better than keyword search, okay? And that system can hopefully digest and give you and recommend you new papers relevant to your research topic, and can be used by a team, and can be used easily to download and integrate into other systems. And that was our motivation at the time to create a new search system by one of the very creative postdocs in my lab at Alot. So this system would take, instead of asking users to provide keywords, what you're going to provide is a dozen articles that contain the topic that are relevant to your topic. Okay, so those would be the only input that list suggest would take. Of course, if you have articles you have already read and you decided to reject and consider that as non-relevant, they can be used perfectly as a negative examples. But negative example is not required. We only need examples of papers that you are interested, and then we can put them together using machine learning. In this case, it's called ensemble learning. Basically, we combine a lot of different specific individual classifiers for improved performance. So once the model is trained, then given a new set of new papers, it can scan the rest of the PubMed or rest of the literature to find you all other papers that are relevant to the seed papers that we provided. And even better is we're going to show you in our web-based interface that this is a paper and how confident the classifier thinks this is relevant to your seed paper. And why is that? And you can also ask you to make a judgment quickly whether this is truly relevant or this is a false positive. Okay, so your feedback is actually very important, because as you start, you only given a few dozen papers, but your feedback is very critical, because these could be near misses, and you can feed them back to the machine learning loop so that the classifier can be better calibrated. And that's exactly what we did with many different projects. And this is one of the projects for cancer research, where when we started as the round one, we already have a pretty good classification performance, about 80%. But as you can see, after 5 rounds of iterations, each time people do a couple manual judgments of the classifier results, we gradually improving that to 90%, which is actually, in my mind, good enough, or actually perhaps even better than human to judge it, because we know 100% or perfect result is not something that a text mining developer is looking for. Okay, and in reality, humans are not doing 100% perfect results. And that's exactly what we used when we created a system called Late COVID back in March 2020, because we want to find all the literatures relevant to COVID-19, and only the literatures about COVID-19. So again, at that time, it was only a few hundred papers, but now, as I said, it now grows very fast to over 250,000. So not only Late COVID collects all the papers about and only about COVID-19, but also for users, to help users to explore the topic, we categorize these papers into different topics. Some of the topics are general, like a mechanism, disease mechanism, treatment, prevention. Some are infectious disease specific, like transmission, like epidemic forecasting, and some are very COVID specific, like long COVID, which is actually, excuse me, the last topic that we added into the Late COVID collection. As you can see in the bottom graph, these topics actually, same paper can be annotated, can be categorized with more than one topic. Okay, the same paper can talk about both the disease mechanism and the treatment. So some of the topics tend to more correlated with each other. You know, at the beginning of the pandemic, basically 2 postdocs and myself, we all looking at all the papers, reading every day what papers, and we annotating these topics manually. But as soon as this literature growth and it takes off, we realize we can't afford to do that. You know, we have other projects, we have other things to do. We cannot spend all our time, all day, all night, just annotating those topics. So that's where we started to thinking about, can we do text mining? You know, that's exactly our expertise is. And in fact, at that time, we already have hundreds of papers, or even more than hundreds of papers, thousands of papers manually annotated. So that directly serves us as a training data for developing machine learning algorithms. And in fact, time goes fast. In just last year, we decided not only we can use that, we can actually provide this valuable manually annotated data for the research community to do a community challenge through BioCreative, which is now, I guess, the longest running community challenge in biomedical text mining community, because it started almost 20 years ago now. So at the last event, workshop, which was held in virtually back in September, workshop in September, about grade 7 event, we had a track to look at called the Late COVID track, where we basically provided our participants training data, where each article is tagged with multiple topics. We ask the system developers, the participants, to develop text mining algorithms to automatically suggest topics, and we can compare, evaluate their computer predicted topics against our humanly annotated topics. Okay, so not too surprising, these days the machine learning algorithm actually performs very well. The best accuracy is now over 90%, which is actually as good as humans can do, because we did some inter-annotated agreement ourselves, and we find, you know, humans can probably only agree as close to 90% as best. No surprising to the audience, if you're familiar with the most recent BERT models, these are the main technique that different teams have been using different variants of the BERT models for this purpose. So that concludes sort of the first part of my talk, which is mainly about getting the papers, relevant papers. And now that you have a set of relevant papers, what can you do for knowledge discovery? Now, we would like to actually getting the entities from the papers and then getting the relationship from the papers. So when we look at the search log of PubMed, we find that the entities that a lot of people are searching are mainly hinged on chemical drugs, diseases, and genes. And that's not surprising because in the end, these are the most relevant, important concepts in biomedical literature. So these are the target type that we are focusing on. In addition, we added genomic variants, mutations, as well as species, because these two are also very important. And here in this slide, I showed you some examples where, as you can see, each concept can be described by different names. Okay, so that just shows you our language, English language, is very rich, but English language is also very ambiguous. Okay, so as you can see from this slide, these are typical English words, but in the context of scientific literature, they can also refer to gene names. Okay, in general, in general books, you probably don't think these are names of a gene, but they are. And here's a concrete example. In this particular PubMed abstract, I'm not dead yet is a gene name, but in other articles, it's not. It's just a regular English words. So we have tried using different methods, and this is a problem that not just our group, and many research groups in the biomedical text mining community are working on, and people have tried different methods. So our method is to using machine learning techniques. So these are a bunch of tools that we have developed over time by two very devoted people in my group, Zhiyong and Robert Lehman. And in fact, these are sort of the very early version of the text mining tools, machine learning tools that we developed. These are mainly hybrid. Machine learning is the main architecture backbone of this method, but then we also supplemented with rule-based systems for improved performance. And we made them all freely available and as an open source tool. So what we found is when we make this freely available as open source tools, they get used by a lot of different people. And a typical use of these software, open source software, is people download them and then apply them to a set of PubMed articles. So realizing this need from our users, we decided, so why don't we actually do this for our community? Why don't we just apply our taggers to the entire set of PubMed articles, okay? And then store the results in the backend and present the results, web front, so that everybody, regardless whether you have the text mining skills or you are just a non-NLP specialist, they can have access to these text mining results, and they can easily integrate that into their working systems. So that's the basic idea of PubTailor. Now it's almost 10 years ago, 10 years old now. So we basically present the text mining tagged results in the abstract and show them in different colors in a web front. As long as you web browser, you can actually look at them. Because as I mentioned, again, text mining is not perfect, but with 80 or 90% of accuracy, this actually could be quite practically useful for different applications. And the user can look at our results for their own assessment so that they can decide whether or not they want to take the next step. And not only they can use the web front, we also provide APIs so that they can easily access our data through the programming programs. And if they really like the PubMed data, we also see a lot of usage of that as well. They can download through FTP. So over time, once we have a lot of usage from different parts of the world, I think including all the continents, mostly, that using API is also the winner here, because a lot of people integrating our results through the APIs. So a lot of users using PubTailor for various things. And one of the things that we use PubTailor for ourselves or for our collaborators is to help them to speed up their data curation. So we have been working with different groups of biological databases, and we have shown repeatedly that NLP can speed up their curation effort, but without any sacrifice in the quality of their end curation results. And whether this is a Swiss part or GWAS catalog, we have seen very similar results outcome, and our PubTailor tool is actually now implemented into their production curation pipeline to speed up their curation process. So because of the success of PubTailor, we decided to make it better by expanding our content. When we first developed PubTailor, we focused on PubMed abstract, and now we decided we can also apply our taggers to full text, which is longer. We have about 3-4 millions of open access full text data in PubMed Central that allow text and data mining. So we integrate those results with the 30 million articles in PubMed, and together we have about over 1 billion annotations, and that continues to grow as we do nightly update to the new articles in PubMed and PubMed Central. So because even though the open access full text is just a fraction of the PubMed database, it's a 3-4 million compared to 30 million, but each full text article is about 10 times, 20 times longer. So together we actually see a big jump in terms of coverage, in terms of annotations we can have for different kind of entity types. And then here I just show you 3, as you can see, adding the full text significantly increase the content coverage in terms of different entity types. Not only that, we have also making improvement in our tagging methods. As I mentioned in the previous slide, when we started doing this, these methods are mainly based on conditional random field. But in the last couple of years, deep learning has really taken off. So we certainly would want to take advantage of that as well. So in this particular paper, we developed our own customized BERT model for biomedical natural language processing, and then compared to the BioBERT model, which is very popular for processing biomedical text, and a set of not only one task, but a set of 10 different tasks, so that we know that a model is actually very generable compared to others. So along with our own method, a thing that is very unique about this work is that we create a sort of a benchmarking data set, which is actually a collection of 10 different data sets, and they represent different tasks in biomedical natural language processing. Okay, so that we can better assess a model's generalizability to different tasks. And along with the methods, we have also improving our tagger with more data corpus. So we have developed a gene corpus. We have developed a new, which including not just a few most important species like human, like mouse, but also I think spans about 10 different or 12 different species. We have developed a new corpus for chemicals from not just looking at the PubMed abstract, but also looking at the full text for named entity recognition. And most recently, we developed a improved version of mutation tagger with more accurate results, as well as more options for normalizing to different database records, including the ClinGen allele registry. So with that, so these are the things that we have put into the second version of PubTailor back in 2019. So we have more accurate. So these new techniques that are combined bring us about 10% percentage point increase in F1 score, which is actually significant, because you can tell the difference between 80% or 70% to 80% accuracy. Okay, if it's 1 or 2%, I wouldn't think that matters that much in a production system, but in 10%, that's actually quite remarkable. We added cell lines and other entity types, and then we also, because API is so popular, we expanded its capacity so that it can allow users to query per query, including 1,000 articles instead of just 100, and then make it a lot faster for our users. So PubTailor is great again, but there are many, but we are only focusing on 5 or 6 different important key concepts: gene, disease, chemicals, drugs, so on and so forth. There are many ontology terms that are around there for biomedical research, and people would love to extract those ontology terms from the literature. And there, PubMed is of little use for that purpose. So here's an example bring up by our colleagues from the NIAID Institute, where they're interested in using, giving a plain text, asking us to extract the ontology terms from phenotypic terms and normalize them into human phenotype ontology, HPO. Okay, so in this slide, I showed you the input and what's the expected output. So to do that, and HPO is an ontology, typical ontology with, I think, over 15,000 terms, and then these terms concepts are arranged in a hierarchical graph or relationship. Okay, so, and each term is actually quite detailed. So there's actually no way, in my mind, that you can ask humans to create a corpus that actually have a good coverage of all the detailed ontological terms in HPO, okay, for machine learning purposes. So what can we do? Well, we can always use a dictionary-based method to start with, okay? But can we use the machine learning? So I didn't think I can, but my postdoc Linor thinks he can, and he's in the audience. So he's very creative, and he thinks that we can do that. So what we did was actually to just create. So we call it weak supervision. Basically, we don't have a typical supervision in manually annotated corpus for machine learning purposes. Instead, we create a training data for machine learning just based on ontology itself. Okay, so and in terms of the performance, I don't go into details, but you can look at that paper. But in terms of performance, you can see here compared to the dictionary-based method, it improves a lot in terms of recall, and that's what we expect, because dictionary-based methods would only find terms that exactly match the dictionary record, names and synonyms. So, but also we are also nice to see that we have no loss in precision. Okay, in fact, we have gained somewhat in precision as well. And so this is very encouraging for us and lead us to actually not only looking at literature, but also using this for electronic medical records data set as well for phenotyping the patient data. So so not only we showed success in HPO, the human phenotype ontology, we actually did another research on a disease ontology. I think in MISMESH we used, and we showed, as long as it's a hierarchical structure ontology, this method would work as well. So potentially this could work with many other ontology terms. It's the same method. So this is something that I want to talk to you about based on for concept recognition and linking. So you can use PubMed for those mainly used ontology term concept types like genes, chemicals. You don't have to do anything. But if you are looking for a particular ontology that do not have a well-established corpus yet, then you think about using the methods presented here in the phenotyper. And last part of my talk will be focused on information retrieval, information extraction. So with these ontology or with this concept extract, what can we do for extracting a relationship between these concepts? So here's an example where we would love to turn the papers in free text into a relational table about gene, disease, and variants. Okay, and that's a real need for us. And in this particular case, you can very clearly see that the gene, disease, and the variant are all mentioned next to each other in the title. So but this is a toy example, okay? Because in reality, what you're going to see is you'll have multiple diseases, multiple genes, and multiple variants in the same article, and across different sentences. And then on top of that, you'll see negations also mentioned in the article to add in the complexity of your relation extraction task. So what can we do? Well, if we look at the literature, again, the performance of relation extraction system has a wide range between 30% to 80%. And why is that? Because if you look at that, the performance really varies based on methods and data set. If you're looking at a performance of 30%, 40%, high percent, 80, 70%, that's probably based on machine learning. Well, if that on the low end is probably based on rule-based and the pattern matching, which means there's no available annotated data set. So machine learning method can perform better, but it does require a lot of training data manually annotated. And most of the relation extraction method, unfortunately, can do well with machine learning on one particular task for protein-protein interaction or disease drug-drug interaction, but it's not really generalizable to another different relation type. So that motivated us to create a new corpus that we recently did to actually contain more than just one relation type. Okay, and we call this BioRed, rich large-scale document level relation extraction data set, which we again focus on 5 different entity types. These entity types have different relations in between them, and also including them between themselves as well. And between a pair of 2 entities, they can have also different relations. Okay, it could be a positive correlation, or it could be a negative. It could be inhibition. It could be increasing. Okay, so annotating a data set like this is very tedious and very costly, to be honest. And also because we want to making sure that the quality is good, so that every article is actually annotated by 2 different annotators. Okay, but luckily, at least there's one thing in our favor is we have a great annotation tool previously developed for other projects that we could reuse in this case, which is called TeamTag. So in this particular tool, it's seamlessly integrated with PubMed and PMC articles. So if you just provide a PMID or PMC ID, you can render the article immediately. It allows computer pre-annotation, so we can display the PubTator annotations, even though it's not perfect, but as a jump start. It does support if your annotation article document is not PubMed articles, it does support free text, plain text, or PDFs. It can be used on a web-based system on your browser, but if you have sensitive data, private documents that you would like to annotate, you can actually download the software and install on your local end to do that. So we have this, so this saved us a lot of time. But still, we spent about 2,000 annotator time hours for this particular BioRed corpus. So in the end, what we have is about 600 articles today, where we have about 20,000 different entities and 7,000 different relations between those entities. So what's more a novel aspect of this particular data set is we take this set and we had a discussion with our colleagues at NCATS, where they were actually about to organize a NLP challenge called the Litecoin challenge for their constituent. And what they like to do is, they want to annotate the relationship as novel or background. This is very novel by itself, because a lot of the relations have been repeatedly mentioned, asserted in the literature, because these are used as a background information. In this case, the relationship between PCSK9 and the cholesterol is the background information, background relation. Well, the novel one is the mutation and the disease. So after we finished our relation annotation, we add another layer of categorizing the relation or the relation to novel and background. And what we find is about 2/3 of the relations that we annotated previously are novel and 1/3 are background. So using this corpus, we can benchmarking different NLP tools for different relation types at once. We don't have to build each individual text mining tool model for each individual relation type. Instead, we benchmarking models for all the relations at once, and we chose two tools. One is called BERT-DT, which developed by our own group, and then the PubMed BERT, which is the newest variant of the BERT model by Microsoft. As you can see, if we just asking the systems to pick up the pairs of two entities, we can have the state-of-art performance is about 70%, okay? And that varies between different types of the entity types, relations, okay? But if we say, not only you have to find the two entity pair correctly, you also have to tell me, is it inhibition, or is it prevention, or is it a treatment? Then that drops to about 60%, the best model. And if we add another layer, if we want me to ask whether this is novel or this is a background information, and then that further making the problem more challenging, so the results is only about 50% at this point. So it's promising in the way that it gives us, this is really an open problem for the research community to work on at this point. And also another use of BioRed is that, you may not, the reason we created a corpus of multiple relations because we want to develop a model that can address all of them together. But if you're only interested in extracting relation of one particular type, let's say protein-protein interaction or drug-drug interaction, you can sort of using BioRed as a boost for your own research. So here I showed you 3 different data sets that has been developed previously for different relation types like drug-drug interaction or protein-protein interaction, drug-protein, and you can see most cases, in 2 of the 3 cases, adding BioRed as an additional data set for training can really boost the performance by quite a bit. So there are many other NLP applications that coming from our group that I'm not sharing. We don't have time to share today, but these are 3 I'm worth mentioning a very few words. So we have using text mining for extracting variants and finding relationships with diseases and drugs, and we are fully integrated our system called LitVar into the DB-SNP and ClinVar, and now also working with ClinGen group as well. We also did a quite interesting study with the NHGRI researchers to allow them using NLP to allow them to scan the literature for the usage of language in terms of ethnicity, race in the genomics research papers, okay? And for all the papers that has been collected and published in the American Journal of Human Genetics journal. And lastly, it's something that that came up from my group recently in the last couple of years, is that when we're working with clinical data, we're taking advantage of our expertise in machine learning and AI for both NLP and image processing together. So when we have 2 modalities together, we tend to have a better performance for disease prediction and risk prediction, so on and so forth. So to conclude and summarize, I've showed you some of the tools, mostly coming from my lab for information retrieval, PubMed, ListSuggest, and the COVID. I showed you 2 tools for entity recognition. One is PubTator, which focuses on 6 different entity types, and then there's a general tool called Phenotaggr that can be used for ontology term extraction. I showed you our efforts on relation extraction, including a tool called TeamTat for annotating different documents, corpus, which is important for building machine learning methods, as well as the most recently published BioRed data set. So our work benefited from a lot of our collaborators, both within and outside NIH. And I'll end my talk here and happy to take your questions. And if you're a student in the lab, or if you're a faculty, have a student graduating, feel free to contact us. We have research positions available at the National Library of Medicine. Thank you so much.
Thank you. Any questions?
Yeah. Okay, thank you for your talk. I have one specific question with respect to the text annotation and the ontology use. There was, maybe you remember also around 2006, this notion of PubMed, that basically you overlay the PubMed in that case it was the terms of the gene ontology. Basically you use the text annotation or ontology annotation of the text to help classify the articles. It got defunct afterwards, but it was quite nice. And I was wondering if you had looked into that and you had realized that wouldn't work, that therefore it hasn't featured here, or may that be something to look into again, so you won't have only keyword-based search, but you also have, in that sense, ontology-based search for that to enhance that, because it seems that it should be possible with some of the technologies that you already have proposed. Maybe you have some ideas to share about that.
Yeah. Well, thank you. Thank you for a very interesting question. So I think the question is, now that you have ability to index articles with concepts, can you actually search with concept terms? In fact, PubMed has been doing that for a long time. If you know that there is mesh terms, which is ontology in a way, and it's not a Go term, it's a mesh term. It's, but that's something that the indexing term at the library has been using manually, actually indexing them, until most recently they decided they want to go also a leveraged computation method. But my point is, but when you look at how people search, people are not necessarily search using concept terms. For the reasons is they're not familiar. As a general user, they're not familiar with concept terms. How many people actually can search with mesh terms? Not to mention, the Go terms, for example. If you're research in this particular area, certainly you're familiar with a branch of the Go term, you can do that. But most of the time, when people search, they're not searching. They're not searching with the ontology terms. Instead, they're using free text. So that's something we see a difference, discriminating between what user potentially think that's important, but when they do search, they search differently. Okay, so the best way is actually, in my mind, is you allow users to search freely. They can search with their free keywords, but at the same time, you automatically recognize there's a concept that show in the user query, okay, and immediately linking that concept to the articles that indexed with that concept. So that's, I think, maybe a better way to go than directly supporting search by concepts, because I don't just that's not a lot of users would use in the end.
Okay, thank you very much for a great talk. I think my question is very well aligned with the previous one. I have also a question about keyword search, and you mentioned that for the evaluation of the methods, you used user clicks, and actually how it's related to the mesh term. So you could assume that if in the keyword search there is a mesh term, and then this mesh term, of course, appears in the paper annotations, do the users actually click on those papers? Is it correlated?
Yeah. So the
Hi there. I'm so sorry to interrupt. I just wanted to let you know that you are muted now. I'm trying to click unmute for you if you can just accept it. Thank you.
Can you hear us now?
Yes, we can. Thank you so much.
All right. So Yeah, so article is index, so its usage is various, I would say, because if we think of articles is in the past where a lot of articles don't have any keyword, some articles in PubMed don't even have abstract, so additional words, additional concepts attached to the metadata is very important. But when article is available, has the abstract, and has the full text sometimes, the contribution of a mesh term as addition may not be so significant in terms of retrieval.
When I search for some paper in PubMed, usually I'm using just few keywords, sometimes one or two words. So, so at least how many keywords should be input for the best match?
That's a very hard question. What I can tell, I can't tell you what's optimal, but I can tell you what's typical. When we look at the PubMed search logs, we analyzed, and typical search term is about 3 to 4 words. So that's what most users use. So remember, even though best match is an alternative to the data sort order, but they both return the same number of articles. In terms of the size of the return set, it just they are ranked different order, okay? And the tricky thing is about the number of keywords is if you adding more keywords, your query becomes more specific. So you narrow down your search scope. So you tend to have less number of articles returned. And that's always the case because PubMed still requires, at this point, the returned articles matching all your keywords. So if we have 5 keywords, all those keywords will be returned or be matched against the article so that that article can be returned. So that I would say you're starting with the ones that are specific, but if we don't get results, if you may get 0 result, and you're starting to relax and remove some keywords so that you expand, so your query becomes more general and you get more results back.
So I think citation graph. The papers are connected on graph format in terms of citation. So what do you think if you use that graph citation for best match searching?
So great question. Why didn't we use citation as a feature or ranking factor? One practical reason is we don't have access to the complete citation. I don't know who has, but we don't. More accurate citation information. So, we have partial citation information at NCBI or NIH because each paper, if it's cited, the cited paper is in PubMed Central, we have that information. But if we look at that citation count, it's a small fraction because not all the papers citing your paper is actually appearing in PubMed or PubMed Central. But I say that this particular feature is also compensated in a way by the past usage of the article. So we have done some analysis, and our internal analysis shows that the citation count is actually correlated with the usage. How many times people is accessed over for a period of time. So in a way, we are using some kind of that information for our ranking, but not directly with the citation.
We have a few minutes left, and we received a number of questions from the online audience.
Sure.
So I'm going to read for you. The first one from Alita Lova. Her question is, do you think you would need to do regular post-tuning for your lead COVID? For example, manually annotating new results once a few months.
Yeah, great question. In fact, we continue to do that, so we maximize our ability to do automating indexing and topic assignment, but as of now, we are still spending time to do manual curation. In fact, what we have done recently find is that, in the past, the problem was a lot of papers, they don't using the word COVID-19, but they actually are COVID papers. but it's the opposite now. All the papers are continuing the word COVID-19, but they're not about COVID research at all. They just, it's like a common word. So we, certainly we do a lot of human curation and we catch those papers, and that becomes another set of our training data for training machine learning models. So yes, I think that's something we are doing regularly to ensure the quality of the system.
Thank you. The second question is from Yingjun Chen. Nice talk. When you evaluate the methodologies such as BioRed for the F1 score for chemical diseases, how do you get the ground truth data? Have you used granularly curated data or other databases such as CPD?
So we do, BioRed has 600 articles, and the results that I reported or showing this slide are based on a subset of 100 of them. Basically, we used 500 for training model development, and the rest 100 as independent set for model testing. So this is exactly based on the human manually annotated data, and our ongoing effort is actually linked here, and we are actually looking at how do we leverage data exactly like CTD for improving our performance.
Great. The last question from Ken Baslendi, and the question is the general one. How would you generally describe the bio-NLP area, especially the area of NLP with biomedical literature? Are there many scientists, and is there a lot of research going on, or is it a niche area?
Well, it's a great area. I've spent all my career in this area, and in fact, there is a ISMB text mining cozy. It's at the ISMB. So just happened yesterday. And there are many researchers in this area that come into the ISMB meeting. Outside of that, we have a community also working on different areas, coming from both computer science and the bioinformatics background. So this is a great area to be in at this point, I think.
Thank you. Any other questions?
So thank you for the great talk. I wanted to ask, did you also try to implement additional information? You said you transitioned from PubMed to PubMed Central, but there are also the information about the tables, the figures, also the supplements.
Mm-hmm.
Did you investigate that?
Yeah. So when I say we transition or we expand our processing from abstract to full text, when I say that, we are already processing the table and figure captions. But in our most recent work with the mutations, we actually go one step beyond. We actually starting to processing supplementary materials, because for that particular concept, 80% of the information is actually in supplementary materials. If you don't do that, you lose a lot of information in that area. So that's something we are already doing. If we don't have to do that, I would avoid, because just too very noisy to work out the supplementary materials. Just there are a wide variety of different ways different types of documents people put into supplementary materials. But yes, when we think this is something we have to do, we will do that, and we have already been doing that. Yes.
Okay, thank you.
Thank you so much for this fantastic overview of this really impressive body of work. I have two technical questions, if I may. You pointed out how key concepts in the biomedical domain are gene names, diseases, and so on. But you also showed the power of modern AI language models. And I was just wondering, most deep language models that I'm aware of are limited by vocabulary size. And I was just wondering, how do you square the fact that we have thousands of genes and many also drug terms? How would you technically approach this to bring these key concepts into a deep language model context?
So, so actually, I think that when we're using the verb model, we mainly looking at the context rather than the word itself. You know, the context, the contextual information is the more important for finding a particular term, or what is this likely to be a gene name here versus is this typically to be a chemical names. And when we do that, we do, you know, it's not like that wide of space because we're looking at the space of English language, basically. What's tricky is once we find that mention, and then we have to link that into the dictionary record. And when we do that, that step is not typically done by deep learning at this point, is sometimes by rule-based matching. It could be done by machine learning, but we're not doing that for the moment. But mostly when I present here, we're talking about using the deep learning for finding the gene names in this case. And in that part, we don't necessarily need the name of the genes.
Okay, thank you. And my second question is kind of related. I'm very impressed by the improvement that you get from the best match algorithm where you re-rank from the click frequencies. However, I was wondering, this still limits discovery to something that the underlying first search, the BM25, gives you the top 1,000. So have you got any thoughts or ambitions in using more modern or AI-based methods to get this first ranking? So for instance, if you're looking for a query that has very few true positives, if they don't come up in the first 1,000 with BM25, you'll never see them. So are there any ideas or ambitions in rethinking search in the context of text mining and the AI?
That's a great question. Yes, we have started looking at that, but we haven't, nothing has been really implemented. None. And on the other hand, BM25, even though it's a decade-old technique, but still serves us fairly well as a first pass. Okay, like you said, you know, we're only using best match to rank the 1,000 document or 500 documents. And when we look at the recall of those 500 returned by BM25, it's actually pretty good. It's 80% plus recall. So if there are other methods that we can use for AI, more recent AI that we can use, we certainly would. So that's something that we will continue to do research on, I think. Thank you so much for the suggestion.